What is going on, Algebra Bros? It's Mr. C here, and in this video we're going to determine the solution space of the following linear system, which by the way is a homogeneous linear system. And as the theorem preceding this example says, the solution set of a homogeneous system AX equals 0 is a subspace of Rn. In this case, our solution space to this homogeneous linear system is going to be a subspace of R3. To start figuring out what the solution space is, we're going to augment or write this system in augmented matrix format. So first row is going to have the entries 5, -6, 1, and 0. Second row will be 30, -36, 6, and 0. Then -25, 30, -5, and 0. And what we're going to do is RREF that, and I'll provide that for you. The first row is 1, -6 fifths, 1 fifth, and then 0. And then rows 2 and 3 consist entirely of zeros. So it turns out that we might need some parametric equations here. In particular, there will be two parameters. Let's keep in mind that the first column is for the variable x, second column is for y, and third column is for z. So what row 1 tells us in this matrix is that x minus 6 fifths y plus 1 fifth z equals 0. Now with the equation this way, I'm going to do a couple of things. All right. This is equivalent to saying that x minus 0 minus 6 fifths times y minus 0 plus 1 fifth times z minus 0 equals 0. This would represent the point normal version or component form of a plane. So it should be clear that our solution space is a plane. In particular, it's a plane that contains the point 0, 0, 0. So based on this version of our solution, we can conclude that this is a plane through the origin. Okay, that's one way of arriving at the solution space of the linear system. Another way is to look at this from parametric equation format, which can then be brought to vector equation format. So to start with the parametric equations, we're going to need two parameters. We're going to need a parameter for the variable y and the variable z. So I'm going to say let y equal t and z equals s. Second thing we do is plug these parameters into our equation from row 1 from the RREF matrix. So it's x minus 6 fifths t plus 1 fifth s equals 0. And solving for x, we get x equals 6 fifths t minus 1 fifth s. And so the parametric equations, or the PE style of this solution, would go x equals 6 fifths t minus 1 fifth s, y equals t, and z equals s. Okay, so the fact that these parametric equations involve two different parameters should lead you to conclude that this is a plane. How would you know that it's a plane through the origin, though? Well, you could write each one of these parametric equations involving the origin. We could write the first equation as 0 plus 6 fifths t minus 1 fifth s. Second equation as 0 plus t. And then the third equation as 0 plus s. And so these would be the components of the vector that's involved when you write the parametric equation version of the plane through the origin. You could also write the solution in vector equation format. So let's say that this represents the set of all solutions x to the system. Using the parametric equations that we just defined above, we could replace x with 6/5 t, I'm sorry, 6/5 t minus 1/5 s, the variable y with t, and the variable z with s. Now, my claim is that this vector that's on the right-hand side could actually be written as the sum of three vectors. The first vector being 0, 0, 0, being added to a second vector, which will involve the parameter t. I'll put t in front of an ordered triple here. It'd be 6/5, comma 1, comma 0. The third vector is going to involve the parameter s, and I'm going to put it out in front of an ordered triple here as well. The components of it would be -1/5, 0, and 1. And this is the vector form for the equation of a plane, namely the equation of a plane that's going through the origin. So either way you slice it, the solution space is a plane through the origin. But if you have any questions regarding anything from this video, feel free to let me know. Otherwise, I'll catch you in the next one. Thanks for watching.